We saw the iron lung last time, and just a little bit more about that, because the iron lung is actually pretty interesting. Uh, I suppose they still use them, although, mainly they used it for polio because people would be very weak and they just wouldn't have the muscle strength to breathe. Remember, we said that we breathe by our diaphragm or the muscles in our chest cavity, that they open up the chest cavity, increasing the volume, lowering the pressure by Boyle's law, and then that forces the high pressure air from the outside to go into the low pressure area of your lungs. And then to breathe out, it closes the chest cavity or makes it smaller, decreasing the volume, increasing the pressure, and it expels the high pressure air that is now inside your chest. And so the iron lung is a solution for when your muscles just aren't able to change the shape of your chest cavity. And we saw that video last time. Iron lung looks something like this. Your person, they have their head sticking out here, and then they lay down inside. And what happens is that the pressure goes up. Would that be exhale or inhale? When the pressure inside the iron lung, would that cause them to exhale or inhale? It causes them to exhale, right? When you have a high pressure inside, uh, when P inside goes up, that's when you exhale, and when P inside decreases, so that you have a low pressure inside the thing, that causes you to inhale. You can think of it too like a potato chip bag. You ever been on an airplane with a potato chip bag? You go up to high altitude and the pressure in the cabin decreases a little bit. I mean, it's a pressurized cabin, but it does decrease a little bit because you're at such high altitude. That potato chip bag will sort of swell up. And in a similar way, your body sort of swells up when you have this decrease in pressure. Your body gets bigger and brings in that air from the outside. So the iron lung is a nice application then of Boyle's law. I understand they also use like hyperbaric chambers. I don't know if y'all have ever encountered anything like that. Do you? They use that for healing from injuries or whatever. A hyperbaric chamber is a high pressure chamber. Like baric is like in barometer. Anybody ever seen a hyperbaric chamber? No. I've never encountered them either. But all right. I had a model of the eye, and I sent it to my daughter's third grade class. And would you know that third grade teacher has not returned my model of the eye? I sort of woke up this morning and said, "Hey, where's my big eye?" But I'll bring it next time. We're going to spend quite a bit more time on the eye later in the optics section. But on this section, we're just going to talk about the fluids in the eye, how we measure those fluids, or measure the pressures of those fluids, and what they do. So the intraocular pressure, that is the pressure inside the eye. This is eye, this is inside. So this is just the pressure inside the eye. Uh, there's fluid that fills the eye, and I will describe those and what those are and what they do, but the pressure inside the eye is just the pressure of that fluid. You can have a couple of different problems with this. If you have high pressure, that's called glaucoma. That can cause issues in the eye. If you have low pressure, which is less common, I think, but you can have a collapse of the eyeball. I'm not sure if y'all have ever known anybody that that's happened to. Do you? No, I'm not sure that's very common, but we know people with glaucoma, or many of us do. Older people will get glaucoma because the pressure becomes too big inside of the eye. There's several parts to the eye. As I said, we're going to talk about the optics of the eye later. But the cornea is that outer part. It's where the light first comes into the eye. It just the outer surface. And then the aqueous humor and the vitreous humor. The aqueous humor is sort of like in this area, as opposed to the vitreous humor, excuse me, vitreous humor, not the virtuous. That's different. The vitreous humor, which is the fluid inside the big part of the eyeball. The aqueous humor is replenished and drains. The vitreous humor is not replenished, and it holds the spherical shape of the eye. I mean, I think that's fairly remarkable that basically the vitreous humor that you're born with, you keep your whole life. It's not replenished. It doesn't drain. There's maybe there's some small changes in it, but it's not like the aqueous humor that is continually replenished and drains. The lens focuses light on the retina. As I said, we'll have a whole section on that towards the end of the semester. And the retina it detects the light. For the purpose of this chapter, y'all, we're really concerned about these two because these are the fluids and we'll be concerned about the pressures. But we're going to see these other things. If you're not familiar with them, it might be sort of a good idea to become a little bit familiar with them right now, just the different parts of the eye. But we'll see those later. You understand what I'm saying? So for the next test, make sure that you understand these two, what they are and what they do. We use I think this is on your quiz actually, a tonometer to measure pressure in the eye. It measures the force required to bend the cornea. Some of you, if you go to an optometrist, they've used a tonometer. Am I correct? You use a tonometer at the optometrist? Yeah. It sometimes it just sort of blows like a little bit of air. Or in some tonometers, they actually have a little pin that comes out and touches your cornea and measures the force. I have a little video I want to show you. It's a veterinarian video, but it's a guy that he's selling this tonometer or he's, marketing it for some pharmaceutical company. But he does it on his little beagle. It's kind of cool. You want to watch it? Yeah. So remember, a tonometer is just used to measure the force or the pressure of the fluid in the eye. Let's see. Right. It's to measure the pressure of the fluid in your eye. Do you like that? I've never had it done. Is it the worst? Yeah. Is it scary? You need to tell them to get one of these things like your local vet uses, or just go to your vet and they can do an eye test for you. All right. All right. Let's see. The aqueous humor. Remember that is the fluid up here. It's that fluid that's replenished. It's the fluid between the um, the cornea and the lens. It's replenished if the drainage is blocked, the pressure becomes too big, and that can damage the optic nerve. The optic nerve runs from the eye to the brain, so it's sort of back here, running to the brain. It can damage the optic nerve, um, and this is called. Gosh, what was this called? This condition, glaucoma, right? And you can use medicines, or you can have surgery to actually increase the drainage of that comes out of your eye. All right. So just know glaucoma, know what those various conditions are for high or low pressure, what the effects of them are, know what you use to measure pressure, know those basic parts of the eye and where the fluids are. Okay? All right, awesome. All right, for the brain, we have several protections for the brain. We have obviously the skull, and I have a funny story to tell you about the skull here in just a moment, but this includes the cranial and the facial bones. And obviously, you can have injuries that actually affect the skull, right? Some of you may have even encountered those. I have a story. It wasn't, I was okay in the end, but it's still kind of an interesting story. Do you guys want to hear it? It's sort of tangentially related to this. But before I was married with my wife, we were, getting to know one another. And we were in graduate school. I was on the 17th floor and she was on the 15th floor. We take the stairs back and forth. But I like to do this thing because, it was kind of cool where I could start up at the top stair and jump all the way down to to the next landing. It was like 10 steps. And it was pretty cool. It was like one of those parkour guys, right? Except not quite as good as that. But I would jump from the top step all the way down to the bottom. And so one day, I'm with her and I'm like, hey, watch this. And she'd never seen it before. So she was about, of course, to be amazed. She's like, wow, this guy is so athletic and agile and just cool. Like, he's a cool guy. Um, so I jumped down, but I never jumped on this particular flight. And there was this ledge that sort of came down that caught me right here, right on the skull, which protects your brain, of course. And it knocked me back, and somehow I didn't hit the back of my head. I'm not sure what happened exactly. But I was able to get up, and I was a little bit dazed, and I looked at her, and of course, she's terrified because she's about to marry me, and she's like, this guy's going to die. And as she's looking at me, blood just started dripping down because a lot of blood in your head it bleeds very easily. Blood started dripping down my nose, and I was like, I gotta save some face, so I said I gotta go, and I run down to the 13th floor where we had a shower, and I just got in the shower and just let all the blood run down the drain while I rinsed it out. Yeah, and it took me a good 45 minutes to get all cleaned up. In the meantime, of course, she's like he's passed out somewhere down in the men's bathroom, dying, bleeding out into the bathroom drain. But obviously everything worked out okay, and she came out like even though I came off looking like a doofus, she still thought that I was something. All right. Anyway, your skull protects your brain. Um, you also have outside of your skull, you have the meninges. Am I pronouncing that correctly? Health profession. Meninges. Okay. Is that meninge? Meninges? Like ninja, but ninji? I know, right? Meninges. All right. These are three membranes that cover the brain, and these contain. I don't remember what these contain. I think they contain. I don't have it in my notes. I think they contain blood vessels, right, to bring nutrients to the brain. Oh yes, these contain the CSF. Thank you. That's the cerebral spinal fluid. It's like I had a brain injury when I was like 22, so uh, and so the CSF um, cushions the brain. It acts to cushion the brain, and it regulates blood flow. And you typically have about 150 milliliters, or about a three-quarter cup of CSF in your brain, or in your head. All right. See, I have a little video to show you. Should I start this back? Yeah. Okay, so just know there's different protections for the brain. Um, you can have problems that occur with the production of or lack of, or I'm sorry, these blanks weren't supposed to be here. The production of the CSF or the lack of production. That is, you can have too much or too little. And this creates pressure in the cranium, and that pressure is called intracranial pressure. A couple of conditions, hydrocephalus. It's just an abnormal accumulation of this cerebral spinal fluid in the brain, and a lack of CSF can also cause problems. The brain can bump up against, as it showed in the video, the brain can bump up against the cranial bones, and as I understand, that can be very painful when the brain actually touches the side of the skull. All right, I have this diagram, but you don't need to know these different parts, like the ventricles. I just really want you to know, the skull, the brain, the CSF. the meninges as well, those membranes that contain that CSF. Ready? Bladder. Bladder can hold about 500 milliliters or more of fluid. When it reaches about 200 milliliters, this is interesting. I don't know if y'all knew this. A person feels an urge to go, like to go to the bathroom. You know what I mean? Because of nerve signals given to the brain at this pressure. So it's like you have this pressure sensor, basically, through the nervous system that will send a signal to the brain like, hey, we're about half full down here. We need to go to the bathroom. But the thing is, if you wait a little while, it'll eventually go away. So if you get that urge and then you just sort of push on through, then you'll be okay. But then if you add another, let's see, 200 milliliters or so, then the urge comes again. I always tell this to my kids when on road trips. They're like, we gotta go to the bathroom. I tell them, no, you just gotta wait because you're only about half full. So you just get that first urge, and then if you push on through, then it'll go away, and then it'll come back later, and that's when you really gotta go to the bathroom. But that doesn't always work with kids because they don't really always think about those various bodily signals that we need to take care of. All right, the pressure for this urge, the pressure is about 30 centimeters of H2O. Or if you're looking at millimeters of mercury, it's about 22 millimeters of mercury. Remember, we're talking about the column of the mercury or the column of the water. Notice, by the way, that the column of the water is much higher than the column of mercury. We talked about this. It's because, right, the mercury is a lot more wet than water. It's what? Viscous? It is more viscous, you're right. And because it's more viscous, it's also more dense. So I just need a little bitty column of mercury that'll be the same weight as a big column of water. That's why these distances are so much different. Pregnant women feel a greater um, urge to go because of outside pressure by the baby. I mean, I've obviously never been pregnant, but my wife has, and she says that affects you. I'm not sure if any of y'all have, but this external pressure increases the pressure of the enclosed fluid in the bladder. And remember, we talked about this earlier, but this is an application of Pascal's law, or Pascal's principle, that when you apply an external force to a fluid, then that pressure is felt throughout. So even though you might not have the full 200 or 400 milliliters of pressure, but you might not have this 30 centimeters of H2O, you might just have, say, 20 centimeters, that baby comes along and pushes on your bladder. It increases the pressure of the fluid the inside the bladder. So it's Pascal's principle there. Alrighty. Let's see, bones. I'm going to talk about stress and strain. We saw this last time. We are not last time, but some time ago when we were talking about stress and pressure. Uh, Stress causes strain. So stress is a force per unit area. It's sort of like the pressure that we've been talking about, though we've been talking about pressure in fluids, but it's still the same calculation that you have a certain force applied over a certain area on a solid, and that causes a stress. That is the force per unit area. And this causes a strain. A strain is a deformation of the solid. Sometimes it'll actually cause the solid to break. So if I have, you know, if I apply a force per unit area to this paper clip, The strain is that it actually moves. I can stretch something like a rubber band, that would be the strain. The point is here that stress, which is our force per unit area, actually causes a strain. Stress causes a strain. Bone mass density measures the strength of bones. The book talks about this. Usually you get your peak bone density in a person's, say, 20s, about when you're about your age, most of you, many of you. All right. And I think, especially for women, I don't know, you probably know more about this than me, but for women, you have to watch your bone density, that sometimes it can be lacking because of, I know, why is that? I don't know. Hormonal things? The short end of the deal or something? What? I don't know. It doesn't really matter right here. Bum deal? No. Oh, y'all are awesome to be women. All right, so osteoporosis, um, the bone density is reduced and more susceptible to breakage. Alrighty, let's try some of these clicker questions. Most of this stuff is pretty straightforward, am I right? Most of it you probably already know even, so um, because of your other classes. Let's do this first one. Tonometer is used to measure pressure in which of these? All right, we'll stop at 35. I'm going to do the others if you like. We'll do the next one to the right. Okay, awesome. But that was on your quiz, so I'm not going to give you a joke for that one, all right? But we'll do this next one. All right, I'll stop at 18, 18. Okay, awesome. Yeah, too much CSF is called hydrocephalus. This isn't a joke. It's just sort of an alarming story. But did you hear that they, no, I'm serious, actually. Did you hear they had a kidnapping down at Thibodeau Elementary the other day? Yeah, he woke up though. It's okay. Then he woke up. All right. Yeah. All right, let's try this one on the left. Glaucoma is the result of which of these? All right, I'll stop in just a few seconds. 24. Man, y'all are getting these like nothing. It's the high pressure and the aqueous humor. We do this one more. Which part of the eye is continuously replenished? All right, I'll stop at 18, 19. Yeah, aqueous humor. That's right, right. Yeah, aqueous humor. I get them mixed up sometimes, but y'all should not on the test, okay? All right, let's see. This is really just a question. Do you think that a kangaroo, a kangaroo, can it jump higher than the Empire State Building? What do you think? Of course it can. The Empire State Building can't jump. Are you crazy? All right, let's move on to work and energy. In this chapter, the first part of the section, which we'll have a test on this in Thursday, a reading quiz on the entire chapter. Right? Reading quiz on 1 week from today, the entire chapter 3. The first part of this, we just sort of do basic stuff about what is work and how does that relate to energy, what is kinetic energy, what are different kinds of potential energy. We'll look at conservation of energy and the work energy theorem. So we'll see those things. And then in the second part of the chapter, we look at how the body takes energy and uses it to make mechanical motion, like to make motion and to have, the body actually move. We'll also look at metabolism and how the body uses energy and that how that affects, the food that we eat and sort of the the type of body that we have. So we'll look at energy, work, and metabolism. Uh, Energy is the potential is the energy to do work or the ability to do work, and work is done when a force causes a displacement. So in fact, we have two things that contribute. We have both force and displacement when we're considering work. And you have to have both of those. If you have no force, but you have a displacement, there's no work done. If you have no displacement, but you have a force, there's no work done. You have to have both the force and the displacement. All right. I'm going to give you the equation for that down here. So work is the product of our force and our displacement, or F times D. So if any one of those is 0, then you're not going to have work. So for example, if I apply a force to this table but it doesn't move, I'm applying a force right now, but I'm not doing any work. Right? And also, if I have something that moves, but I'm not applying a force to it, then I'm not doing any work on that object. Now there is a force that's doing work on this object. What force is that? After I push it, yeah, the frictional force is, the wheels are turning and there's friction in the bearings and all that. So there is a force that's doing work on that object, but I'm not doing any work. All right, so if an object has force but no displacement, there is no work. And if you want to think of displacement as distance, a motion, a moving from one position to another, that's fine. But I'll use that word to talk about how an object moves from one position to another position. That's our displacement. Sometimes people use distance for that word as well. So, and if an object is moving, then it must have had work applied to it. Uh, so if I have an object moving at a constant speed, yeah, Stephanie. Well, not necessarily. At some point, it would have had a force acting upon it. But Newton's first law says that if you have something that's moving and there are no forces acting upon it, then it will continue moving, forever. So if I have an object moving, it doesn't necessarily have to have a force acting on it at that time. If it's moving, it had a force act on it at some point in history, but at that time, not necessarily have a force acting on it. Okay? That's a good question. So that goes to what we're saying here. Uh, Yeah, that's what I said just now. So if an object is moving according to the first law and it continues moving as it is, at constant speed, then there are no forces acting upon it. And work is the product of the displacement and the component of the force that's in the same direction. So what that means is that our force and our displacement are in the same direction. So right here, my displacement is in this direction because I'm moving from this position over to this position. And so my displacement is to the right. But notice that my force is in this direction. We talked about early on, I think in chapter 1, that there were vectors sometimes in 2 dimensions, and that these vectors actually had 2 different components. Remember, like with the hack squat, we said that you don't lift as much as is on the bar because you only really lift a component of that vector. You recall that? It's an inclined plane. It's a simple machine. In a similar way here, we have 2 components of this force vector. We have one component that is in that direction and one component that's in this direction. We can think of it as like a triangle. It is a triangle, in fact. that looks like this. This is my x component, this is my y component, and then this is my force vector. So I have these two different components, and only one of these components actually does work on the object. Which component does work? This component that's pointing up, or this component that's pointing to the side? Up or to the side? Right, the one pointing to the side. Because the one pointing to the side is in the same direction, or it's parallel to the force. So when I want to have a force that does work, then I want to have them to be in the same direction. All right, so for example, I can push this table in two ways, or I can pull it in two ways. I can pull it like this, or I can pull it like this. Now, which one requires a smaller force that I exert? The one that pulls like this, or the one that pulls like this? This, the second one, actually, because if I want to actually move it in this direction, I want to do work on it in this direction. If I pull like this, I have one force that's pulling up. That one doesn't do any work at all. It doesn't cause it to move at all. It just pulls up. That's just sort of lost energy, if you will, because I'm not doing anything with that force. But I really want to get down here and pull in that direction so that all of the force is parallel to the displacement. Okay? With me on that. We'll see some questions about it later. But now there's one other thing that has to do with the direction of the force. Uh, if the force is in the same direction as the displacement, the work is positive. If the force is in the opposite direction of the displacement, the work is negative. And if the force is perpendicular to the displacement, the work is zero. Um, you can write this down if you want, but you don't have to. You're not going to see it again. Well, I'll take that back. The actual equation for work is that work is equal to FD times cosine of theta. And that cosine theta term, it takes the component and puts them in the same direction. So cosine of theta is always less than 1, and it's equal to 1 if you have 0 degrees. So when theta is 0 degrees, that is they're in the same direction and they're parallel to one another, this just equals 1, and I get the maximum amount of work. But if I have a certain angle, such that like I'm pulling it like this, then the cosine of that angle is always less than 1. That decreases the amount of work that the force does. Okay? I know that's really exciting, but let's look at some scenarios. Let's say that I have an object that's moving in this direction, so my displacement is in this direction, and I want to know, is the work A, B, or C, is the work positive, negative, or 0? And my force in this case that's doing the work is in this direction. Is that work that that force is doing positive, negative, or 0? We'll do a few of these, but first let's do this one. Is the work positive, negative, or 0? All right, let's stop at, say, 28. I'll go to 30. Okay, it is positive here. Uh, Part of the force, it's a little misleading because part of the force actually does 0 work, but it does positive work as well. So remember, we can break it into two components. I have the force that goes here, and then also a component that goes here. This part does work equals 0, but this does a positive work. So we would say that that force does positive work. Part of it doesn't do any work at all, but overall it does a positive value for work. Let's say that I have an object here, and I have a force that's in this direction. So it's still moving to the right, but it's got a force that's acting to the left. That would be sort of like me pushing the chair, right? It's moving to the right, but the frictional force is pushing back in this direction. All right, so does that do positive, negative, or zero work? That force. Does it work do positive, negative, or zero work? All right, I'm going to stop at 25, 6. Okay, good. You're starting to get it. So this one is negative work. Why is it negative work? It's going the opposite direction. So uh, the sign for the work doesn't have anything to do with the direction of the work, because work doesn't really have direction. The sign indicates whether the force is taking away or giving energy. That's spelled right? Doesn't look right. It's right. Takes away or gives energy to the system. Or, increases the energy. So for example, with the chair, if I push on it in this direction, the displacement is in that direction. Positive or negative work? The force that's done by my hand? That's positive work. I'm giving it energy. But the frictional force is opposite the direction, and it's taking away energy. That's why it comes to stop. And that's why Aristotle thought that things, had this natural state of rest. So friction is often something that takes away. So this is often friction. Because friction opposes the direction of motion. You probably have some questions. I'll, give you similar things or ask you, what type of work does a frictional force do? It does negative work. It takes energy away from a system. Or if I push on something, that does positive work because I'm giving energy to the system. I'm making it move faster. Positive and negative work just relates to how I give or take away energy. All right, here we have 4 blocks. Which force does no work? The first question, is it A, B, C, or D? Which force does no work? A, B, C, or D? Oh, and they're all moving to the left. So each of these blocks are moving in this direction to the left. Which force does no work? No, it says each move to the left. So, but these are just 4 forces. Some of them actually might point to the right, like here, but there are other forces involved too. But I just want to know which of these forces does no work at all with the object moving to the left. You understand the question? All right, let's see how y'all doing this first one. All right. I'll stop at 103, 104. Okay, A is right. It does no work because it's perpendicular to the force. I mean, to the displacement. The force and the displacement are perpendicular. Which does negative work here? Moving to the left, which of these forces does negative work? All 4 blocks are moving to the left. Which does negative work? We'll stop at 28. Okay, C is right. It does negative work because the displacement's in one direction, but the force is in the other direction. If you like pushing this and the frictional force is in this direction, the displacement is in that direction. So that frictional force takes away energy, causing it to stop. Negative work is caused by a force and a displacement that are in opposite directions. Which does positive work? Number 3. All right, I'm going to stop at 32. Okay, so the one that does positive work is B. Why does it do positive work? That when the force and the displacement are in the same direction, that means that that force does positive work. And here, I have the force in this direction and my displacement in this direction, and so I'm doing positive work. I think some of you might be confused because, you know what I've done? I've put my displacement to be negative, right? We usually take left to be negative. Maybe that's is that why some of you are confused about this? Oh yeah, D. Yes, D would also be positive. Okay, you're correct. D is also positive. All right, because it also has a component at least that moves in this direction. Okay, I can't put two answers though. I'm sorry. It's not a big deal. And then which force does the most work? All forces have the same magnitude. It's just there are various, orientations. Which force does the most work? Which force gives the object the most energy? All right, we're gonna stop at 20, at 30. Okay. Um, why do y'all think it's B? You know, explain. It's not. It's B, but maybe the question isn't worded right. In order to get the maximum amount of work, you have to have the force and the displacement in the same direction. So, for example, with D, I have one component of this force that's in that direction, and one component in this direction, and this force does no work. This force does work, but it's less than the amount of work that's done by that. You with me on this? I'm not convinced completely, but in short, though, if our forces are a force and displacement are in the same direction, then I do positive work. If it's at an angle, then I still do positive work like this if they're, in the same direction, but I do less work because part of the force does no work at all. And if I'm in an opposite direction, then I do negative work. So you don't really have those three scenarios. At an angle, I do decreased amount of work. In the same direction, positive, opposite, negative work. Are y'all just tired of sitting here for an hour? Is that the thing? Okay. Well, I'm gonna move on. We're gonna go on to the next topic. Is that okay? All right. Let's see. Negative work takes energy away. Said this already. Positive work gives energy to an object, or transfers energy if you want to be more technical about it. Okay. Is it possible to do work in an object that remains at rest? going to stop at 25. Okay, no, because remember work is force times displacement. If either force or displacement is zero, and if it's at rest, which of those is zero, the force or the displacement? The displacement would be zero. I'm pushing on this table right now, it's not moving. Even though I'm exerting a force, like within my body, I'm using energy in my body, I'm not doing any work because the object's not moving. It's really a definition that we're applying, but it's not doing any work because I require both force and displacement. And then what about this last one? A box is pulled across a rough floor at a constant speed. What is the work done by friction? None, positive, or negative. All right, let's stop at 25, 25. Okay, it is C. All right, if friction does negative work. Why does friction do negative work? Right, friction always opposes motion, almost always. There's very few select situations. All right, well, you can have two forces acting at it. So I'm pulling on this table. It's moving at a constant speed. I'm applying a positive work in this, or a force in this direction, positive work, but the frictional force is applying a force in that direction, giving negative work. And so it's like I'm giving it energy, the friction is taking away energy, and so it's just continuing to move at a constant speed. Okay? Okay. Let's move on to energy. We're going to see some of these ideas again. So if they haven't settled well in your brain, don't worry too much. We'll see them again. Kinetic energy is the energy of motion. You know, like kinesis or kinesiology, motion has to do with things moving. The kinetic energy, this is on your equation sheet, but the kinetic energy is equal to 1/2 mv squared. So if I double my mass at the same speed, I get twice the kinetic energy. But if I double my speed, my kinetic energy increases by what amount? If I double v, the speed, what happens to my kinetic energy? What is it? It increases by 4 because it's a quadratic relationship. If I double this, I quadruple this. Because, 2 squared is equal to 4. M is the mass, V is the speed. If you do work on an object, the energy changes. And this is called the work energy theorem. It says if you do work on an object, you change its energy. Often we'll say that if I do work on an object, I change its kinetic energy. Although, or we use K, don't we? Did I use K before for kinetic energy? Okay, I'll look. Yeah, so we'll use K here. We often say that our work changes our kinetic energy, but your work can also change something else we call potential energy. All right, let's see. I push a car at a constant speed. What is the work done? Is it positive, zero, or negative? I hear the one on the left. I'll stop at 25. 25. Feel free to ask your neighbor if you're uncertain. Okay, good. A is right. It's positive. Because I'm pushing it and moving in the direction that I'm pushing it, so my force and my displacement are in the same direction. And it's positive. And I can also think about this as positive work is I'm increasing the energy of the car. And so that's also positive work. If I was decreasing the energy of the car, if this was negative, then I would be doing negative work. So whatever work I do causes to either increase or decrease the energy of the object. If I do positive work, I increase its energy. If I do negative work, I decrease its energy. Now, which of these is the unit of work? Look back at your equation for work. You know the units for those particular things. Is it Newton meters, meters over newtons, newtons over meters, or meters times newtons over seconds? Okay, very good. Ask your neighbor if you're uncertain. We'll stop at 35. 35. Okay, good. A is right. Uh, Remember, work is force times distance, or displacement. That's going to be newtons times meters. You could see questions like that, especially as we move forward from here. We're going to begin to see more and more units that build on one another. And so you might see more and more of this where I ask you, what are the units? You look at the equation, ask what are the units of those individual things, and then you compare them together. All right? Let's see. The units of work and energy are the same, but work is in Newton meters. I can also say that energy is in Newton meters, but usually we use the joule. So a joule is equal to 1 Newton meter. So usually we use the joule for energy. And sometimes people use the Newton meter for work. Sometimes they use joule. But a Newton meter and a joule are the same. You might have heard joule before. It's the SI or the SI system for energy of food and the like. So you might have seen that. It would be the equivalent of a calorie. Or not the equivalent, but the same measure as a calorie. So you might have seen joules before. It's a measure of energy. All right. Let's look at potential energy. Potential energy, we're going to call this U. So far we have several things. We have W, which is work. We have K, which is kinetic energy. And then we have now U, which is potential energy. And potential energy is stored energy or work. So you can store up energy or work and then use it later, and that's called potential energy. There are lots of different kinds. Where's my rubber band? All right, so rubber band, this stores potential energy, right? As I do work on it, I cause it, I apply this stress, and it moves it to a longer length. It now has energy that if I were to let it go, it would move, right? So it has the potential for motion, or it can move. That's called potential energy. That's elastic potential energy. So that's one type, elastic potential energy. We also have gravitational potential energy. So for example, if I have my keys and I hold them up here and then I let them go, I as I hold them in the Earth's gravitational field, they have the potential for motion. They have stored energy or stored work there. That's called gravitational. We'll talk quite a bit about chemical potential energy as it relates to the body, right? As we eat food, that has energy stored within the chemical bonds between the atoms or molecules that's released by these chemical processes in our body. So we have chemical. There's some other types like nuclear that we'll get to later in the semester, right towards the end. And let's see, I think I got another. Oh, and electric potential energy. So we'll get to all of these, but mainly this chapter, we'll deal with these top three. We'll talk about the mechanical systems where you see these two, and then our food systems, our bodily systems where we use chemical energy. All right, let's say that you move an object of mass m to height h. So I have an object, it has a mass m, and I move it through a height h. I move it up in this direction to height h. What work have I done in order to do so? Remember, work is force times displacement. So you want to ask yourself, what work or what force have I done to move it through that distance h, that displacement h? Is it m times g divided by h, f divided by h, mg times h, or m over g times h? I remember what g is, right? Our acceleration due to gravity. All right, let's stop at 112, 112. A few more seconds. All right, let's see. The answer is C. I apply a force. My force here is equal to mass times gravity. That's just the weight. And then I multiply that force times the height. Work is equal to force times displacement. That's going to be m times g. That comes from my force. My d becomes h. And so that becomes the work that I've done. All right. Give me just a couple more minutes. We'll wrap up. The work has changed the energy of the object. So I've done work on this object, moving it through this distance, and I've given it what we call potential energy, this gravitational potential energy, and this is given by this equation, m times g times h. So we have a couple of things that we've seen. We've seen that work is equal to force times displacement. Kinetic energy is 1/2 mv squared. And now our gravitational potential energy is U is equal to mgh. All those things are on your equation sheet, but next time we'll begin to apply them in a few situations. All right? A rough day. Hey, it's not as rough as my day because this morning I was walking out across the quad and this dude, some student I think, threw a Coke like across the sidewalk and hit me in the head. I was all right though. It was a soft drink. Y'all are suckers. Y'all have a great day, okay? Bye, Taylor.